AP Chemistry. So this is the answers video for day 88, the assignment on rice tables. And so let's go ahead and do this. All right, so the first three questions are on the lecture video. So this question, the one on the next page, or number 2, this one with the N204, and then finally this one. These are all on the lecture video, so watch that to get the answers for this. So let's move on past that. Okay. And we are going to do this one. Okay, so 2SO2 plus O2 produces 2SO3. If the initial concentration of SO2 and O2 are 0.1 molar and the equilibrium concentration of SO3 is 0.075, what is the value of Kc? So what you have in all these problems is this, basically. I'll write it off to the side. You have an equilibrium constant, and what it does is it ties together the concentration of products on the top and the concentration of reactants on the bottom. So that relationship between products and reactants is expressed in this constant. If the products are very large, the concentration is very large compared to reactants, then this is going to be a big number. If the concentration of products is very small compared to reactants, in other words, what we're talking about is what concentration you have on the product side versus the reactant side right here. Okay, so if the concentration of the reactants is large compared to the products, then this number is going to be small. So this number relates the two of them. Okay, so let's go ahead and fill out the table here. So first of all, write the reaction. Okay, and it's not conventional to write the arrow, but I like to do it because I want to be sure I don't forget which side is products and which side is reactants. Okay, now we're going to fill in the boxes just like a little puzzle. So it says we have 0.1 molar of both of these, and that's initial concentration. That's on the I line. So I'm going to write, I don't care about the trailing zeros, I'm just going to write 0.1 and 0.1. All right, there you go. All right, now if they don't give you an initial concentration for something, often it's the products, not always, but often, you can assume it's 0. So you are allowed to assume that. All right, now it does say the equilibrium concentration of SO3 is 0.075, so you go down to the equilibrium line, 0.075. Okay. All right. So now what you need to do, if you're going to find the value of Kc, you need to fill in these two boxes. Everything that goes into the law of mass action is based on equilibrium concentrations, not initial. You use the initial to figure out the equilibrium. All right, so it's we know that if you started at 0 and ended up with 0.075, then the change had to be 0.075. In other words, you started here, you added this, and you came up with this. That's all, just that simple. All right, now, what about the equilibrium concentrations down here? Well, the equilibrium concentrations are going to be, you got some change. Now, what is that change? We don't know. So we, just like in math class, we give it a variable name. It's called x. So there's x. In addition to that, these are reactants. They're going to be used up. They're going to be consumed. Therefore, we put a negative sign here. The third thing we do is we look at what's the coefficient in front of the O2, and although it wasn't written, it's a 1. So we're going to call this 1x. Same thing over here. It's x is the variable, some amount that we don't know yet. It's being decreased, so we put a minus sign here. And then you always use the coefficient in front of whatever that compound is, that in this case the reactant SO2, and it's a 2. All right? So again, this is just simply an addition. 0.1 plus, you could think of as plus or just minus 2x. So the equilibrium is going to be 0.1 minus 2x. This one's going to be 0.1 minus, you could put 1x, or you at this point just put x. So now we have all three equilibrium values, although these two are in algebraic form, so we need to figure out what they are. Well, here's the deal. If this is 2, then if I wrote this in terms of x, this would be 2x. okay, if I were writing in variable form. So this is going to be a 2x because there's a 2 there. So we know that 2x equals 0.75. So I'm just going to come down here and write 2x equals 0.075. Again, let me say that again. I don't want that to be tricky. We actually know the value of this, okay, because we know we went from 0 to this, so this had to be the value. If we were to write it in the variable form that we did here, this would have been 2x, because you'd put an x there. It's a positive because it's a product and it's being produced. It's going up in value, and you always use the coefficient in front of the compound. So this would be 2x. So that means 2x is 0.075. So now let's figure out what x is. So we started doing that right here. We're going to divide both sides by 2. Okay, and we're going to get, okay, and that equals 0.0375. Divide that by that. All right? So that's not our final answer. That's the value of x. So if we actually want to know the concentration of this, we take 0.1 minus 0.0375, our value of x. And what that will give us is 0.0625. Okay, so that's the concentration of O2 at equilibrium. Now what about this one? Same thing. It's going to be 0.1 minus 2 times x, which is 2 times 0.0375. Sorry about that. Okay, so it's 2 times this number that we figured out right here, and that's going to be 0.025. Okay, so now we have all 3 equilibrium values in actual numbers, not algebra anymore. This is the final concentration of the SO2, this is the final concentration of the O2, and this we were already given in the problem for SO3. So now to find Kc, we plug it in. So the first thing I always want you to do, just don't just go to plugging in numbers. Write the equilibrium equation, also known as the law of mass action. So it's Kc equals this on top, so it's the concentration of SO3, and then the coefficient becomes the exponent. Don't put the coefficient inside this though, don't make that mistake, or put it out here. It's just there, that's the only place. Okay, now we have O2, and there's a coefficient of 1, so it's going to be concentration of O2 times concentration of SO2. And you're going to raise that to the second power. So that's our law of mass action. You should always write it in general form like that with the equation rather than plugging in the numbers right away. Okay, so now we do plug in the numbers. We're trying to find Kc. So let's go ahead and plug in our numbers. SO3 is what was given to us. I'm going to switch to parentheses because we're doing a math equation now. It doesn't matter. You can leave it in brackets. Squared over, and then it's going to be this. Okay, there it is. Convince yourself that that is correct, all right, based on this equation and these numbers up here. Okay, so now it's time to do the math on that. And that gives us an answer of 144. That's a fairly large equilibrium constant. It means that this number is going to be, the top number is going to be 144 times the bottom. That means most of the reaction will go over to products over here, all right? It'll come over to this side. Some of it will still stay on this side though. Okay, there is some still there. Okay, so explanation. All right. And so write that as your explanation. I'm not going to write it out, you write it out. Let's be sure you're listening and not just watching the video. Okay, so it means that this means that a fairly large portion or fraction of the products of the reaction will go to the product side. Okay, we'll go over to this side. All right? and a smaller number will stay on this side. Right, so the equilibrium constant relates the products to the reactants and tells you how far to the right or left the reaction is going to move before it finds its happy place and settles in with a certain amount of product, a certain amount of reactant. Okay, the next problem. So we're moving on. There is no problem 5. It was just a skip in the numbering. Okay, so, and there is a correction. It says an initial concentration of 1 molar NH3. Change that to atmosphere. So this is a problem dealing with pressure, not concentration in molarity. Pressure is measured in atmospheres, okay? So it reacts according to the equation. 2NH3 produces N2 plus 3H2. That's a decomposition reaction. It's breaking this into pieces. At equilibrium, the pressure of NH3 is 0.8. What is the Kp? So that's what we're looking for, is the Kp. So first thing we can do is we can write the law of mass action. You should always write it in the equation form before you start plugging in numbers. So I'm going to come here, I'll come down here a little bit and write Kp. Okay, and it's products on top, and it's pressure. So we're not going to write with the square brackets. We're going to write P N2 with a subscript N2. And even the subscript has a subscript, N2. Okay? And you can put a dot here for times for multiplication. And then it's going to be, and I do like to put parentheses around it though, and then it's going to be the H2, the other product. So it's the pressure of H2. And it's raised to the third power. You don't put the 3 inside here and here. You only put it up here. Now we're going to go to the reactants or the denominator, and that's going to be NH3, ammonia, to the second power. Okay, so there you go, and that's your law of mass action. All right, now let's start filling in the rice table. First thing you do is the reaction. Now go ahead and put the coefficient of 1 in front. Not required, but I just like to do it. All right, so let's read what we have. We have an initial concentration of 1 molar, one atmosphere of NH3. So this is going to be a 1. I don't care about the trailing zeros, just 1 is fine. All right, and then it says an equilibrium pressure of NH3 of 0.8. So we actually have numbers for this. But now we need to figure out concentrations over here or rather pressures. If I say concentration, I mean pressure in this problem, because we need to know what to plug in here. So what do we know for the initial pressure? We know nothing, so we're going to put a 0. And we're going to put a 0 here. Okay, we're going to assume that it has none of pressure. The 100% of the pressure in that vessel, that container, is going to be the NH3. None of it's going to be this. All right, now let's write our algebraic equation for all 3 of these. So this starts at 1, it ends up down there, so you're gonna subtract x, and it's because it's a reactant being consumed, being used up, it's going to be a negative sign, and because there's a coefficient of 2 there, it's going to be minus 2x. All right, now this one we don't know what it is, but we know it's a product, so it's going to be going up in value, so it's a plus. It's some unknown value, and since the coefficient is 1, we're going to put a 1 right there. Okay, finally this one, we know it's going to go up by some value of x. It's positive because it's on the product side, it's going to be going up in value, and we have a coefficient of 3, so we put that there. Now let's go ahead and solve this. So 0 plus 1x is 1x. At this point now, I'm just going to call it x. All right, and 0 plus 3x is 3x. Okay, so now what is x? We have no way of knowing it except we have an algebra equation here. And it's this: 1 minus 2x is going to equal 0.8. We were told that's going to be the final equilibrium concentration for NH3, so we're going to put 0.8. Okay, so now what we're going to do is we're going to solve for x. This is basic algebra. Minus 1 and minus 1. This goes away. The minus sign doesn't, sorry. Okay, and that's going to give you negative 2x, and 0.8 minus 1 is negative, negative 0.2, 0.2, okay? Now we're going to divide both sides by negative 2. The negative 2's go away, and what we have is x equals 0.2 over 2. Do that on your calculator, and so that gives you x equals positive 0.1. Okay? If you have trouble with that algebra, come work with me. You don't want to get hung up on the AP exam because you're not strong with your algebra, so please come and see me. So we know what x is now. So what does that mean? It means we now know what this is. This is 0.1 because that's x. And what's this? This is 3 times 0.1, which equals 0.3. So now we know all 3 of the equilibrium values, 0.3, 0.1, and 0.8 that was given to us. Now we're ready to come down here and let's plug it into this equation, okay, to find out what Kp is. So Kp again is the relationship between products and reactants when they find their happy place at equilibrium. So Pn2 at equilibrium is 0.1. And pH2 is 0.3. And NH3 concentration, as was given to us, is 0.8. And you have to square that. And I forgot to raise this to the 3rd power. Okay, be sure to do that. Okay, coefficient. It's right there. It's in this formula at this point. And this one is squared. Okay, so now we're going to do the calculation. So let's do it. I'll do it live here so you can see it. So what I'm going to say is, try to get the glare off of this, is 0.1 times, now remember PEMDAS is going to say that the powers are done first. So I'm going to, and I like to still put it in parentheses. So it's parenthesis 0.3 raised to the 3rd power, close the parenthesis, and now I like to hit an equal sign. Hit equal signs often. Don't try to put the whole equation in at once, especially numerator denominator. That can get a little messy. So it gives us that. Now we're going to divide that by what's in the denominator, which is 0.8 squared. So I'm going to put parenthesis 0.8, and I'm going to square that with my square button right there to the 2nd power. You can see that's a little blurry. Let me fix that. Okay, I'm going to close the parenthesis, and now I'm going to hit equal. And it gives us 0.0042. So Kp is 0.0042. So you can see that equilibrium constants can often be very small numbers. By the way, no units of measure on an equilibrium constant. So what is that telling you? It's telling you that most of this is going to stay as NH3 as the reactant, because it means the denominator is much bigger than the numerator, and that's why you get a very small number. And not very much of it is going to decompose to N2 and H2. In fact, the reaction really wants to go in the other direction. You put these two in a vessel, and they're going to combine to form ammonia. That's what they tend to want to do. So small equilibrium constant means very little in the direction from left to right. Okay, we're on to the next problem. And it says if 0.1 molar of H2 and 0.14 molar of I2 are present initially, and the Kc, the equilibrium constant for concentration, is 2.6 times 10 to the minus 4 molar, that's, no units for equilibrium constant, compute the equilibrium concentration of HI. So there's the equation. Now something to notice here, these are gases, but you can still express them as molarities. They can still have concentrations. Gases do not have to be expressed in terms of pressure. That was a point that confused me once when I was learning this. So that you can have concentrations of gases. Okay, so let's write the equation. And again, I put this in for you, but you should write it anyway if it's not already there, because it's usually not put there in Rice table problems. Okay, there you go there. All right. And I'm going to go ahead and write up here, right next to the equation, the law of mass action. All right, so it's going to be this. And let me put my coefficients on here, by the way, even though you don't have to put ones, and you've already got the 2 there. So here it is. So it's this one on top because it's a product. And I'm going to use square brackets because it is a concentration. And you square it because of the 2. On the bottom, have H2. Coefficient is 1. So we're going to leave no exponent there, and I2. All right, there you go. So that's the law of mass action. Okay, so let's go ahead and let's start figuring out what we can figure out. It's like a little algebra puzzle. Okay, so it says the initial for H2 is 0.1, and for I2 is 0.14. All right, and we don't know HI. It doesn't give us an initial, so we're going to put it as 0. You always do that if they don't give you an initial. Now, this is going to decrease by X. So you put an X, it's decreasing because it's a reactant. You put a minus, and the coefficient is 1 there. I'm going to go ahead and write it here as 1x, minus 1x. Here, same thing. It's going to be an X. It's going to be a minus because it's a reactant on the left side of the arrow, and that's going to be a 1. Okay, so over here we have this, and I'm going to get rid of the 1 now, just write the X. Same thing here. All right, and then over here, it's a product that's going to be increasing. It's X, and since it has a coefficient of 2, it's going to be 2x. So when you add 0 plus 2x, you get 2x. So now we have our algebra to do our algebra equation here, okay? All right, now they do give us a Kc. We couldn't do the problem if they didn't. We're not figuring out Kc. We're using it to figure out what these concentrations are, specifically HI, which is what it asked for. Okay, so let's go ahead and plug that in. You notice this is a fairly small equilibrium constant, 10 to the minus 4. Okay, let's write the equation with the algebra first. So it's going to be this. Now here's the thing. You do write the 2x in here now, because that's actually the concentration is 2x. In addition, you put the exponent up here. All right, so you do write it in both places. Divided by, now in the denominator, we have H2. And you have I2. Okay, so there's your algebra equation. So now we've got to figure out what x is. Okay, so we're going to use the simplifying assumption, because if you multiplied these two together, you would end up with an x squared. All right, and that's going to mean you're going to have an x squared equation. It just means you have to do some integrated math too, and that is use the quadratic formula. Okay, but we're going to use the simplifying assumption. What does that mean? Since we have a very small equilibrium constant, we're going to assume that the change is going to be very small, that x is going to be very small. Okay, so the simplifying assumption is, let's just write it out this one time. It's on your video. Okay, so it says, if the simplifying assumption, if x is very small compared to the initial concentrations, so our initial concentrations are 0.1 and 0.14, we can eliminate x. Now you can eliminate it when you're adding or subtracting. The example I gave in the lecture video was, if you take 1,000,000 and add 5 to it, you get 1,000,005. 1,000,005 is so close to 1,000,000 that you can ignore the 5. You would have to go out 7 significant figures for that 5 to have any impact. So you can basically ignore the 5. Okay, if you subtracted 5, same thing. 1,000,000 minus 5, it'd be a number so close to 1,000,000 that you can ignore the minus 5 and just use the original number, 1,000,000. Now that's not true for multiplication. If you took 1,000,000 times 5, you'd end up with 5,000,000. 5,000,000 is a lot different than just 1,000,000, right? It's 5 times as much. So you can't eliminate the x in a multiplication situation, but you can in an addition situation. So what that means is we're going to take these x's here and get rid of them. Just assume they're not even there. That's true if these x's are very small compared to the initial reactants. Now, which initial reactant? Well, use the smallest one, because that's the one it could most likely be close to, not the bigger of the two. So I'll use the smaller of the two, all right? So now we're going to rewrite the equation down here. So now we're going to square the 2 and square the x, so you get 4x squared. And then down here we're just going to put 0.1. We got rid of the x. And 0.14. We got rid of the x. So now what we're going to do is multiply both sides by these two and divide by 4. Okay, so that's just basic math. That'll give us x squared. So I'm going to go ahead and do that. Okay, so I'm going to come over here and I'm going to write that equals 2.6 times 10 to the negative 4. And we're going to multiply it by this and this, these two. .14. So we multiplied the top here by 0.1 and 0.14. This is just basic algebra. These canceled. And now I multiplied this side by them as well. So there it is right there. And now we divide by 4. So the 4 is going to come down. So it's over 4 here. It's going to cancel here. And we're going to put it over here over 4. So that's what you would end up with. Okay, so 2.6 times 0.1 times 0.14 divided by 4 will give you this, but now you've got to tack back on this. Don't forget that. You left it off just to deal with the coefficients, and now it's times 10 to the negative 4th. And if you take the square root of, square root of that, so square root of x squared is x equals, all right, and we're going to take the square root of that, and that gives us, okay, so what I want to do is take the square root of this. Let me write that a little neater, square root sign. Take the square root of this. Let me show you how I do it on the calculator. It's you don't need to adjust decimals until you're at your final answer, so just leave it like that. So it's going to be second, and then x squared, but that brings up the square root. It's 0.0091 times 10 caret, the little hat symbol right there, to the negative 4. I just type that in. I'm going to close the parenthesis, and it gives us this. And I'm going to write it in decimal form. 0.0003095. So that's the value of x, but that's not your final answer, don't forget. Okay, that's the value of x. Now you're going to come up here, and you want to know the concentration of HI. And it's 2 times x. So it's going to be 2 times 0.00095. Okay, and that's going to equal, I'll write it right here, the final answer. Multiply that by 2, and it's 0.019. And it's molar. It's a concentration, so it's a molarity. So that's it. I kind of wrote it in the margin, but that's the final answer. That's the concentration of HI. Now, let's go down here. It asks you, using the 5% rule, confirm that the simplifying assumption was appropriate. What that means is, was it justified in just dropping these x's like they didn't exist? So if this value, if the value of x, it's not that value, it's the value of x is less than 5% of the original concentrations, then it's justified. So what is the original? Well, you have two different original concentrations, 0.1 and 0.14. So compare it to the smallest of the two, because that's the one it's most likely to be greater than 5% of, is the smaller of these two numbers for concentration. So we're going to come down here and do that, and we're going to get this 0. 0.1 being the concentration of H2, and there's the X value, so this is X, this is concentration of H2. Then you're going to multiply it by 100%. And what does that give us? That gives us 0.95%, which is less than 5%. So eliminating X is justified. You can do it. It doesn't make a significant, doesn't give you a significantly different answer than the quadratic formula. I'll just write is okay. It's okay to do it. All right, that's it for this problem. Okay, now we're on to number 8. This is a problem that I was doing in class and didn't do it successfully because I faked myself out with this. Create a rice table. You do not need a rice table for this problem. It's actually a simple problem. Okay, so it says you have this same reaction we just saw. If the equilibrium concentration of N2 and H2 are 0.5 and 0.1 molar respectively, what is the equilibrium concentration of NH3? Again, let's write the law of mass action. We did it on the last problem. And sometimes you can just generically say K equilibrium. It could be concentration or pressure, but it was concentration on the last one, so let's write it. Again, practice writing these every chance you get. Products on top. Coefficients become exponents. Reactants on bottom. And coefficient is exponent. Okay, well here's the thing. You don't need a rice table. You might want to write one, but it gives you the equilibrium concentrations of these two. Equilibrium concentrations are what you plug into the law of mass action, not initial concentrations. Well, we have the equilibrium concentrations of these two already. And we have the Kc value. They gave it right there. It's K equilibrium. They call it same thing. So that means the only thing we don't know is what we're solving for. And that is the equilibrium concentration of NH3. So it becomes a very simple problem. Let's do the algebra first, and then we'll plug in the numbers. So the algebra here would be to multiply both sides by NH3 squared. Cancels over here. Okay, now we're going to divide both sides by Kc. Cancels over here. And so now we've solved for NH3, which is what we want to know. We're going to have to take a square root, but we solved for it. So let's rewrite it. Now we're ready to plug in the numbers. Okay, so N2, concentration of N2 is 0.5. Again, use square brackets or parentheses, whichever you want. Concentration of H2 is 0.1. I'm pointing up above the screen. It's right there. They were given to you in the question. And you've got to raise that to the third power. And Kc was given to you as well. 3.81. Okay, so now it's just math. Let's go ahead and do the math. And what do we get for that? 0.1 to the third. I'm raising it to the third power. Equals. I'm going to go ahead and hit equal. And then I'm going to multiply it by 0.5. Equals. I like to hit equals a lot. Sure, I don't mash up my numbers, my PEMDAS. And then you're going to divide by 3.81. And that equals 0.00013. There it is. Now we need to take the square root. Let me just rewrite it down here. Okay, take the square root of this side and the square root of this side. That makes this inverse, so you end up with just on the left side NH3, the concentration of NH3. That's what we're looking for. okay, and the square root of 0.00013 gives us this. Okay, oops, and I'm off screen. There it is. I just took the square root, got that. Did I get that right? Yeah, got that right, okay. 0.11, what is that number? What are they asking for? The concentration of NH3, so it's molar. Okay, always put the units of measure. Okay, and that's how you do that one. It didn't require a Rice table, really. If you recognize that you were already given 2 equilibrium concentrations, that's why you use a Rice table, to find out equilibrium concentrations. You didn't need it here. Okay, next. Okay, the next one is review. So let's do a bunch of these together. Okay, so these are ionic bonds. Naming ionic compounds. Let's look at the examples. This is straight off your assignment from about day, I don't know, I'm going to say about day 10 or 15. So again, what you have to do is use your charge number by ion sheet to figure out the charge on these. So sodium is a +1, oxygen is a +2. Remind yourself of what that means. It means sodium wants to lose an electron to be like its nearest noble gas, which would be helium. Oxygen wants to gain 2 electrons to be like its nearest noble gas, which would be helium. So they have full octets and they're happy. So what you do is you take the charge number and you simply swap it over. So in order to have these two balance out, you need 2 1 pluses to balance out with the 1 2 minus. Okay, they have to be positive, negative, have to be the same number, but opposite signs. So you need 2 1 pluses to balance the 1 2 minus. So you just use the crisscrossing arrows. The 2 comes underneath the Na, the 1 comes underneath the O, but of course you don't write it. And it gives you Na2O, and that's sodium oxide. Okay, it's not a covalent bond, so it's not monoxide. That's for covalent bonds. We'll do that on another assignment. Okay, phosphorus. So calcium, again, you got to go to your charge number by ion sheet. Get that sheet out. Don't do this without looking at that sheet. Or just, if you understand how to figure these out, look at a periodic table. Okay, so it's a 2+ for calcium. It wants to lose 2 electrons. Phosphorus wants to gain 3. So you crisscross, there's the charge numbers. You crisscross the arrows, and you have Ca3P2. So you need 3 of the 2 pluses, which equals 6+, to balance out with 2 of the 3 minuses, which is 6-. So 6+, 6-, and that's calcium phosphide. The only thing you change from the names, the calcium, the metal stays the same name. The phosphate changes to phosphide. It changes to IDE. Okay, now, manganese. Okay, so manganese has more than one charge, but this one we're going to use is a 4+. Oxygen is always a 2-. It never has more than one charge. So you're going to go ahead and assign the charges up here. Now, how do you know which one to use? You had to be told that, so you know it's going to be a 4+. Okay, so you crisscross the arrows, and you end up with a 2 here and a 4 here. So that's Mn2O4. But this is an ionic bond, meaning that 2 and that 4 only represent a ratio. It's saying you need 4 oxygens, you need 2 oxygens for every 4 manganese. But you can reduce that. It's not a molecule, it's just a ratio of how many oxygens to manganese atoms. So you're going to reduce it down from 4 to 2 down to 2 to 1, 1 to 2. So manganese 1, O2. Now, since you had more than one possible charge with manganese, and how do you know you did? Go to your charge number by ion sheet. You should be looking at that already. Look at manganese, not magnesium, manganese, and you'll see that you have more than one charge. That means you have to use the Roman numeral. The Roman numeral for 4 is IV. The V is a 5, the I is a 1. When the smaller number comes before the bigger number, it means you subtract. So it's 5 minus 1. So that's manganese 4 oxide is what you would call that. One more with lead. Lead has more than one possible charge. Look at your charge number by ion. Nitrogen can only have one possible charge. So it's a 3-. So you crisscross and you get a Pb3N2. All right. So in other words, you need 3 of the 2 pluses, which equals 6+, to balance with 2 of the 3 minuses, which is 6 minus. 6 minus 6 plus balances. Now, since you can't reduce 2 and 3 the way you could 4 and 2, it's just going to stay as Pb, 3, and 2. And since the lead had a 2 plus charge, it's not how many lead atoms, it's the charge on them. It's going to be lead 2 nitride. Okay, so do the rest. I'm not going to do answers video on this. You can ask me in class, but these examples should be sufficient. If there's only one charge to the metal, I left it blank. You go figure that one out. If there's more than one possible charge to the metal, then I wrote down which one I want you to use. Okay? All right, that takes care of this answers video, and we'll see you in class.